We are currently headed towards ecological disaster. The increase in greenhouse gas emissions globally causing a large increase in our global temperature, increasing the risk of dramatic weather events and wildfires seen all over. To avoid climatological disaster, we are going to need to hit our net zero emission targets. We can no longer rely on fossil fuels as the key source of our energy. Cleaner and greener alternative fuels are needed, and one possible candidate for this is hydrogen. Hydrogen is an extremely energy-dense molecule. It is 3 times more energy-dense than gasoline. It is the most abundant element in the universe. And what's more is when we burn hydrogen or put it through a fuel cell to extract the energy that we want, the only emission we get is water. There's no CO2. Moreover, we can generate our own hydrogen in a clean and green manner. By using the energy generated from solar and wind farms, we can use this to split water back open, reduce the hydrogen, and create a nice, green, economical circle. However, the practical implementation of this fuel source is somewhat hindered and limited by the hydrogen storage problem. Unfortunately, hydrogen exists as a gas across most accessible temperatures and pressures, which means we need really big vessels to store it in, really bulky ones. A 5.5 litre jerry can of diesel or gasoline, petrol, the equivalent for hydrogen storage is a 60 litre vessel under 700 atmospheres. Now, clearly, we need to find a better solution, a more compact solution. If we could have hydrogen as a liquid or a gas, then this would solve it, but they only form at extremely low temperatures or extremely high pressures. If we could only manipulate the phase diagram and let them form at higher temperatures and pressures, then perhaps we could solve this. And that's where my research comes in. I have been looking what happens to hydrogen when you put it in a really small vessel or space. And to do this, I've been using a material called highly microporous activated carbon. Now, to you and me, this is basically charcoal with really small pores. And you can think of it like a molecular sponge that soaks up these tiny molecules of hydrogen. But what's interesting is when we dose it with hydrogen gas, what was found was that the amount of hydrogen packed inside these pores appears to be at a density higher than solid hydrogen at temperatures and pressures where hydrogen should be a gas. And this begs the question, is solid hydrogen forming? Is it forming in these pores? And if so, why? If we can understand why this is happening, then perhaps we can reverse engineer the process and help us solve this hydrogen storage problem to get compact solutions. So this is what my research has set out to do. And to do this, I've gone to the particle accelerators and neutron sources in both Oxford and Grenoble to study my materials under pressure and temperature. So I took the highly microporous carbon or sponge, dosed it with hydrogen across various temperatures and pressures, and for the first time we were able to prove and show that solid crystalline hydrogen does form in the pores, and a very unique one as well, quite exotic. But more importantly, I was able to show that this solid forms at 5 times higher temperature than it would outside of the pores, which is fantastic. Not satisfied with this, I wanted to understand why. To do this, I studied the rotations of hydrogen. Hydrogen loves to rotate. Even in the solid state, it's rotating. So much you can imagine it in a spherical-like motion. When you put it in these very small spaces, those rotations begin to hinder. It rotates in a more 2D or 1D-like fashion. This allows the molecules to align and also increases the thermal stability of these solid phases, making them more thermally stable. Now, with this knowledge that I am now armed with, I hope to take my research further to reverse engineer other materials further to try and get this compact hydrogen at higher temperatures and lower pressures to help solve the hydrogen storage problem, to help our globe and planet reach its net zero target.